Let's look at exercise 17 from section 1.9. We have an inequality that involves a rational expression. We want to move all terms to one side of the inequality, leaving 0 on the other side. And we want to write the numerator and denominator in completely factored form. So I'm going to subtract 5 from both sides of the inequality. And then I want to get this as a single rational expression. So both terms need to have the same denominator. So I'm going to multiply 5 by x plus 4 over x plus 4. And that's still greater than or equal to 0. And so now I'm going to go ahead and simplify this by putting the subtraction over the common denominator, x plus 4. So once the denominator is common, we simply put both expressions over that denominator. All right, now I'm going to go ahead and carry out the subtraction by first distributing. So minus 5 times x is minus 5x. Minus 5 times positive 4 is minus 20. And I recopy the denominator, and that's still greater than or equal to 0. 35 minus 20 is 15. So this becomes 15 minus 5x over the sum x plus 4 is greater than or equal to 0. So I can factor out a negative 5. Out of the numerator. And to make sure that's clear, let me first reorder this. Instead of writing the minus 5x second, I'm going to write that as the first term. Instead of writing positive 15 as the first term, I'm going to write it as the second term. And then this may make more sense when I factor out a minus 5. Minus 5 times x gives me my minus 5x. Minus 5 times negative 3 gives me my positive 15. And that's over x plus 4. So I want to factor this completely. So minus 5 is multiplied times the x minus 3, and the denominator is x plus 4. And that's greater than or equal to 0. So that is factored completely now. I'll write this a little neater and make the box a little bigger. All right, so that's the first thing that I needed to fill in this problem. All right, now I want to find the boundary points of this inequality. And I do that by setting the numerator, which is minus 5 times x minus 3 equal to 0. And since the minus 5 does not involve the variable and is a factor, I can divide both sides of this equation by minus 5. And I'll get the same solutions that I would have gotten if I didn't divide by the minus 5. And so now I'm simply left with, when we're finding boundary points, we want to set the numerator to 0. And so I'm now solving x minus 3 equals to 0, which means, of course, x has to be 3. All right, now that gives me one boundary point. And that's the boundary point in the numerator. So if the numerator is 0 and the denominator isn't, the expression is equal to 0. So x equal 3 is actually part of the solution. Now I'm going to set x plus 4, the denominator, equal to 0. And that will be true if x is negative 4. So my boundary points are, I'm going to put them in number line order. Negative 4 is the smallest, so I'll write that first. 3 is our larger boundary point, so we'll write that first. So we want to set up our test intervals in order to find the solution to this rational inequality. I'm going to start by drawing a number line. Now remember, negative 4 made the inequality undefined because it gave me a 0 in the denominator, so that's not included. I'll leave an open circle where negative 4 is. 3 makes the denominator 7 and the numerator 0. So that's actually going to be when the expression is 0. So 3 is part of the solution. So I make a solid circle above 3. And here are the intervals that I need to test. So I want all the numbers to the left of negative 4, all the numbers between negative 4 and 3, all the numbers bigger than 3. So I set up the intervals that represent all the numbers that are not test numbers. That's why all of these that are not boundary numbers. That's why all of these intervals don't include the boundary numbers. And I pick a number that lies in each interval. Negative 5 lies in the first interval, 0 in the second, and 4 in the third interval. And I'm going to rewrite my inequality here. And I'm going to let negative 5 represent all the numbers that are smaller than negative 4. Whatever negative 5 does to the inequality, all the numbers in that interval do the same thing to that inequality. So I wind up getting 40 over negative 1, which is negative 40. And the inequality winds up being negative 40 greater than or equal to 0, which is false. Negative 40 is less than 0. So the inequality is false, so all the numbers in this test interval from negative infinity to negative 4 make the inequality false. So now we're using 0 to represent the second interval, and we wind up with 15 over 4 greater than or equal to 0. And that's a true statement. So our test number 0 shows us what all the numbers in our interval do to the inequality. All the numbers in this interval will make the inequality true. Now let's test 4, which is the representative for the third interval. And we get negative 5/8 greater than or equal to 0, which is false because negative 5/8 is less than 0. So notice that the inequality, negative 5 over x times x minus 3 over x plus 4 greater than or equal to 0, is true when x is an element of the interval negative 4, 3, including 3. So notice that negative 4 is not included, but the 3 is. 3 makes the expression 0. Negative 4 makes the expression undefined. So I put a square bracket next to the 3. So my solution then is the interval that contains all the numbers between negative 4 and 3 and includes 3. And just a reminder, this symbol means is an element of.